So next speaker is Pascal Lauer, and he will present work together with Antoine Lin and Pascal Bercher on tight bounds for lifted HTN plan verification and bounded plan existence. Please.
Okay, as Daniel said, I'm Pascal Lauer. This is joint work with Antoine and Pascal Bercher. And I'm gonna summarize our results on the complexity analysis of lifted HTN plan verification and bounded plan existence. So how all of this started is basically I read a paper of Antoine, Connie, Maite, and Pascal, and they analyzed plan verification and bounded plan existence on different task representations. And if you look at the bottom row, which represents lifted HTN, it's not done yet. So they only identified the lower bound and the upper bound, but not the actual completeness result. So I felt like somebody should fix that, and I started the task connected with Antoine, and we were able to do so. Okay, so I threw a lot of words at you, and I think we should start to understand these words. And starting with what the actual task structure is. So what does lifted HTN mean? Given that you're in the HTN session and have just heard a talk about HTN, you might be familiar with it, but just to give you a rough intuition in case not, how I usually think about it is basically that you take a classical planning task and you add an additional solution constraint, which kind of identifies a pattern in your plan. And lifted basically means that we consider the user provided input as is. So we have schematic action schemas and methods. In HTN, we refer to this input typically as an HDDL. In classical planning, the equivalent would be PDDL. Okay, so to get closer to what really this hierarchy is, I wanted to look at a running example. And we planning guys really like our logistics examples. We love driving trucks, right? So consider an example where you have a logistics company, you want to do all the things you already modeled in your classical planning task to drive trucks, but now the EU forces you to also plant a tree for every truck you drive. And maybe planting trees is complicated, so you want to make it an action which also has certain constraints. So how we would model this is to have an action plant tree on top of the drive action and then one compound task which describes this behavior to be EU conform. And to describe what being EU conform means, we describe this with methods which basically tell us we can either drive a truck and plant a tree at the same time or keep on doing multiple EU conform tasks. So to then figure out what this pattern looks like, we start with one initial task, which could be our EU conform task, and then we can apply methods like we want until we have only actions in our task network. So for example, we could first apply our method to get to EU conform tasks and then get to 2 drive action and 2 plan tree actions. Theoretically, we could also impose some ordering constraints within the methods, and then in our final method, we want to find some serialization that obeys the ordering constraints. Since I didn't put any here, we can, for example, find the plan tree, and then drive action. Okay, so what's an action? An action in our setting is a simple strips action. If you consider a grounded one, so like really just doing one fixed thing, driving from A to B, this would just have your precondition to say something needs to be in the state, the add list to add something to the state and delete something from the state. Now, typically, this is not how the user describes it. How the user would describe it is in a schematic fashion that we say we have multiple objects for the locations, and then we describe which locations are adjacent to each other. And basically, these variables, which I mark with a question mark, act as placeholders for our objects. The same would hold for our methods, so we would also, in a lifted setting, describe our methods in a schematic way. Basically, the task which we replace, we call the head of the method, and the tasks we obtain, we call the body. I think I messed up the L2 and L3 here. The L3 should be in the middle. Basically, what I try to emphasize here is that The compound tasks are also just like predicates. For example, here we could enforce that we have an initial starting location, the location L1, and an ending location L2, and then just add locations in the middle, and so can add more structure to this hierarchy. Then, as I said, we could also impose ordering constraints through the methods. So for example, here we could say that all tasks we obtain from our task T1 EU coform must be coming before the other task T2. But this doesn't need to be the case, so the other method also works without any ordering constraints. So what are the decision problems we look at? I guess it's quite intuitive from the name. Plan verification means I'm given a task and I'm given an action sequence. Is it really a plan? The reason for this, the reason why you would consider this is kind of obvious. I don't really trust your planner, so I want to verify that the plan is really a plan if you tell me. And also, with respect to plan existence, there's always this idea that we could just guess and check something and then verify if whatever we guessed is a plan. So there's an implicit link to plan existence. Then we considered two different bounded plan existence problem. The difference is in the bound we consider, basically in how we encode our bound. Either it's unary or it's binary, and I think the unary one is like the most interesting problem we are looking at. The reason for this is that I kind of have the hot take that this is the most important plan existence problem you could consider. I will explain this on the next slide. And the binary existence problem in the literature typically is referred to as a weaker version of optimal planning, and you can use it for a nice comparison to the unary bounded plan existence problem. So why am I saying that this unary bounded plan existence problem is so important? If we speak of complexity analysis, typically what we do is we take an input and we want to make a decision if something is true or false. But a planner doesn't really work like this. If we ask a planner for a plan, we want to output some sequence of actions, and these actions take space. And this is very much like a unary encoding. So we kind of have the expectation that there needs to be some runtime allocated for actually outputting these action sequences. And I think in terms of complexity theory, inputting this as a unary bound really makes sense. So if you would frame the problem differently and would say our plan needs to be bounded by some polynomial, this is just equivalent to enumerating this polynomial and providing it as input. Okay, so just for completeness, I will not go through all of these bullet points, but I showed you this matrix in the beginning. Basically, all the little sets were not just built up by Sanct One, but there's a lot of work leading to this. I just wanted to give credit there. Okay, so to fix the last row, what we did is identify that plan verification for lifted HTN planning is in X time, so X time complete. And unary bounded plan existence is the same thing. It's X time complete, and binary bounded plan existence is next time complete. Now you could say, cool, table filled, job done, that's it. But I kind of feel like usually we want to get to a low complexity, and if you compare these results to classical planning, it's quite far off, and we were trying to understand why this is the case and get a more fine-grained analysis if we constrain HTN further. So kind of the question is, what makes this so complicated? And I think if I say, well, HTN consists of these two components that we either that we find the plan in the classical setting and we go through these actions and we can decompose it. An intuitive question is, why don't we just bound the hierarchy? If we can impose a bound on our action sequence, why not on the decomposition depth? And personally, I don't think that's as intuitive, because in general, our HTN planner is not required to output this hierarchy. He could just output the plan and do something very smart in the background to transform this hierarchy and not be bound to actually using the hierarchy itself. So for example, in our running example, this could be realized by just using this equation, right? We just want the plan tree to be the same amount as the drive actions. And this is a lot easier to do than to do all of these decompositions. But if we look at the structure of our task, one thing we can realize is that because we never delete tasks, actually we know a certain length of our action sequence given by the current size of our task network. And this is because in our example task, we don't delete any compound task, and in the end, we always decompose to these two actions. So we are always increasing the plan length and building this up. So there is some relation between what our methods look like and what the action length is. And so we opted for looking at this instead. We defined the method size to be the number of body elements a method decomposes to, and analyzed the cases where you can delete things and cases where you cannot. And we actually identified that for plan verification and unary bounded plan existence, this really decreases complexity. And I guess these cases greater or equal than 0 and greater or equal 1 are kind of intuitive. We really realized this difference of we are allowed to delete something or not. So we realized, wow, the intuition really holds. This makes things easier. And this equal ones is kind of tricky. It's very much a toy case, but it also tells us something, because intuitively what it tells us is that there's still some complexity hidden in even just decomposing one linear path repeatedly in this lifted task structure. So it points at a new direction where you could get rid of complexity. Okay. So to sum this up, we looked at two more things that could increase this complexity. And the first was task insertion, hierarchical task network planning. You can see this as kind of a relaxation of the original HTN constraints, in the sense that instead of the whole sequence, instead of decomposing the initial task work to the whole sequence that is the plan, that you just need to find a subsequence which you can obtain from your initial task network. And the reason why we would think this makes it easier is that for the unbounded plan existence problem, the complexity drops from being undecidable to being decidable. And the other thing we looked at are these different ordering constraints. So if we would pose certain types of orderings and would consider the very much border cases where everything is ordered or nothing is ordered at all, we have a similar effect. So in general, it's undecidable, but in the total order case, it's X time complete, and in the unordered case, it's piece-based complete. So kind of from the unordered plan existence problem, we would guess that these constraints somehow affect complexity. But what we found is actually for our case, this is not, and I think this really highlights the difference in the unary bounded plan existence problem, and that you could also consider these differences algorithmically. So kind of, if you have in mind that there's some bound on your plan, you might be able to make different assumptions in your algorithm and so plan more efficiently. Okay, to give you a last intuition of what the proofs actually look like and where some of the complexity comes from, I just wanted to quickly give you this picture. If you have ever seen like a reduction from a Turing machine to data log or lifted classical planning, this is kind of similar, because you could do the same with a predicate. So basically what you can do is use your compound tasks as a piece-based bounded Turing tape, and then model the transitions via your heads in the method, and then just decompose to the new Turing state. So yeah, to sum up, we identified the complexity for lifted HTN plan verification and bounded plan existence under different ordering constraints and method size constraints. We found fragments with reduced complexity, but I think there's more to do, so you could further study this. In particular, I would be interested in really looking at these things where certain method structures relate to the plan length, and also to the thing I've just shown you, how the size, how the number of parameters in your compound task affects the complexity. Thank you.
Yeah, thank you. Thank you for the talk. Other questions? So I was wondering if you see, any from your proofs and so on, from your things you thought about, if you see any implications for practical verifying plans. So because in principle, from my experience, if you ground like the fragment that might be, so I mean, you start with a plan, so you have your constants given, and you can really base on that your grounding, and so grounding for me was not the bottleneck in my head. Do you see any like advantages, anything to learn from this for practical verification?
I'm not sure if I can follow the question, but so one thing I was thinking about, if you look at the initial table, yeah, so we see that it's X time complete. And the way I got there was very much that I had very many intuitions that I felt like are quite alike to data log, because this decomposition in the lifted level really kind of resembles if you do data log regression. So like you start with one task, which is very much like a predicate, and then you can apply a rule which adds certain body elements which are very much like the rule elements. So I could imagine if you that this very much points at data log encoding you could use if you look at how we verify things. If this will be more efficient, right? It's always very hard to actually theorize about what will happen in practice. Yeah, I don't know.
Sure, thank you. Other questions?
A little bit of a dumb question, just coming out of the field, or coming out of a different field. What is the difference between unary and bounded in this case? Well, just in terms of meaning.
Unary and binary bounded. I didn't get a question,
like so, is it a difference in how you encode your problems, or is it?
Okay, so it's really, if you look at this thing, right?
Yep.
The input, instead of just being the planning task,
Yep.
would literally be a sequence of ones, or an n given in 1 and 0. And so like the idea is that, at least if you come from the classical classical planning background, like this bound is basically non-constraining. So in classical planning, you always have a upper bound on the plan length. And then like the unary and binary, the only difference would be how much runtime you would add extra. So in a sense, how you could think about it is if you measure the runtime of a program, you can either say, I want to measure the runtime of my program just in the input, or I want to measure it in the input and output. And the binary and unary, it kind of resembles this difference. The unary one would say, I give you enough tape sets on my Turing machine in the input, so that, and I bound the output size, so I know what the output will be. Whereas the binary one doesn't give you that because it's binary encoded.
I'll have to talk to you after the break, just a bit about that, but I'll take it.
Okay, let's thank the speaker again.